In this video, I'm going to demonstrate how to carry out a principal components analysis using SPSS. Principal components analysis is basically utilized when you have a larger set of measured variables and you want to reduce those down to a smaller set of components. Oftentimes, components analysis is a precursor to other types of analyses like regression analysis or MANOVA, where you may have a larger set of predictor variables or outcome variables in the context of MANOVA. And if you have a fair amount of intercorrelation among the variables and you're running the risk of collinearity among those variables, then you may want to reduce that set of variables down to a smaller set for inclusion in those analyses. PCA is also utilized in the context of exploratory factor analysis. Oftentimes it's sort of a precursor to identifying a set of factors or determining the number of factors that may be present in the data, and then you might follow that up by carrying out traditional EFA using something like principal axis factor analysis or maximum likelihood or those types of things. Some argue that PCA is an acceptable alternative to standard exploratory factor analysis, but there's a lot of debate on that. So I'm mainly going to treat PCA from the standpoint as a technique for data reduction only, and leave the argument about using it for standard exploratory factor analysis for others to argue. So at any rate, we have a data set right here. It has 100 observations. We have a set of variables with subject matter interest, mastery goals, perceived utility, anxiousness or anxiety, performance avoidance goals, and work avoidance. And I also have a kind of an achievement variable here if I was going to be reducing a set of sort of motivational variables down to a smaller set of variables, and then including those derived variables as predictors of achievement. I could certainly do that. So what I'm going to do is I'm going to mainly focus on carrying out the PCA using these variables here. So each row in our data set contains responses to a set of measures for a given person, and then again each column contains a separate measured variable in the data set. So what we'll do to carry out the PCA, we're going to go to Analyze, go down to Dimension Reduction, and click on Factor. And I'm just going to reset this and do this over. So we'll highlight all of our variables that we want to include in the components analysis. So I've got all of my variables included, and I'm going to go to descriptives, and I'll ask for univariate descriptives. Some other things you might ask for, KMO and Bartlett's test, maybe the determinant, and we'll just kind of stick with that. We'll click on Continue, and under Extraction you'll see the method is principal components. We'll click on Scree plot, and then we'll leave the eigenvalue rule as it is. So you have to keep in mind that basically when we are deriving a component solution, the basic idea is we're taking this larger set of variables and trying to reduce them down to a smaller set. And so the original set of variables all are correlated to some extent. And the idea is that what we're trying to do is to explain the total variation in the set of those measured variables. And part of the variation is overlapping or shared variation. And so what we're trying to do is to derive a set of components that help to summarize the overall variation in the measured variables. So the components essentially are derived variables based on the variance and covariance of the original set of measured variables. And so we'll talk about how that works. So there are several decision rules that decisions that you have to make when you are carrying out a components analysis. First is the question of how many components should we retain to summarize the pattern of variances and covariances among the measured variables. So we have to make a decision about how many to retain. And then second, once we've decided on how many to retain, then we have to give meaning to those components. So we have to name them, or describe them in some way to give them meaning. It's not just enough to say, hey, we retain 2 components out of this set of measured variables and then stop. It's not very informative. So we have to, describe or name those components, and we do that by looking or studying the relationships between the measured variables and those components. So the first question really of how many components should we retain, there are several decision rules that are decision strategies that one can adopt to decide. In SPSS, you'll see that we have several things. We have a Scree plot, which gives us a visual way of representing the variance that's being accounted for in the measured variables, and I'll show you that in a second. And then based on that plot, we can sort of decide on how many components best summarize the variance in the original set of measured variables. And then shave off components that are more trivial in terms of explaining that variation. Another decision strategy is to utilize a rule that's called the Kaiser criterion, or the eigenvalue cutoff rule. And so in this case, it basically involves retaining those components that have an eigenvalue that is greater than 1. And so these rules these approaches don't always agree. Sometimes they can kind of disagree. And this is where your interpretation really comes into play. There's a little bit more of subjectivity when it comes to looking at the Scree plot, whereas the eigenvalue cutoff rule really kind of follows the same strategy that we might use when we're testing for statistical significance, and we establish an alpha level and say at this cut point we retain a null or reject a null. So the eigenvalue cutoff rule essentially establishes a cut point for the number of components to retain. So there are obviously problems that can be associated with that particular strategy. Another approach to deciding on how many to is another technique that is called parallel analysis. So parallel analysis is essentially a strategy that involves, it's essentially a simulation approach where you generate eigenvalues from randomly generated correlation matrices containing the same sample size and the same number of variables. And then essentially we plot those random eigenvalues, and then at the point at which those random eigenvalues fall below the eigenvalues in your data, at that point we retain the eigenvalues that are falling below those eigenvalues from your data. So I'll show you that in this presentation as well. Finally, a couple of decisional approaches is that you might decide on a number of components and then perform some type of rotation and then try to interpret the loadings and determine that certain components are really indescribable, or there's not enough measured variables that load on those, in which case an inability to name the components or something like that would also factor into the question of how many as well. So I know this was kind of a long-winded discussion, but it's kind of important because you have to make that decision first of how many components to retain. So we're going to stick with method principal components. Just keep in mind that there are other types of approaches, and this the other approaches that you see right here are associated with standard exploratory factor analysis. So I'm going to stick with the defaults in here and click on continue, and you'll notice right here it says rotation, and a lot of times when people are running their analyses with these interfaces like SPSS, they just end up clicking a bunch of buttons and they don't really know what they're doing, so they might click on Varimax or Promax rotation or something like that. And typically, the strategy really starts with deciding on how many components to retain, and then once you've decided on that, then sort of forcing that solution and then interpreting the rotated solution. So I'm actually going to leave this as none, because right now I'm going to, I'd rather you learn or think about this in terms of steps rather than button pushing. So we'll start off with just a couple of approaches to identifying the number of components. So we'll click on OK. And so looking at our output, you can see, we have the means and standard deviations for each of the measured variables, as well as the sample sizes. So we have a listwise deletion sample of 100. I think there were no missing data points, so it's not different from what we already had. We have down here, we have the KMO and Bartlett's test. KMO is referring to the Kaiser-Meyer-Olkin measure of sampling adequacy, which is this right here. And this is sort of, really what these two tests are addressing is the question of whether it's appropriate to even carry out, analysis of a given correlation matrix. So, the basic idea is that, if your correlation matrix, let's say we had our measured variables, and your correlation matrix will have ones along the principal diagonal, and then you would have correlations on the off diagonal. And if those correlations were around 0 or near 0, then trying to run a components analysis or even exploratory factor analysis using something like components analysis is really pretty irrelevant. So you have to have a matrix that is reasonably factorable in order to perform the analysis and have it make any kind of sense. So these indices are really kind of getting at that particular question. So the KMO is just a descriptive index, and basically a value that is less than 0.6 might be considered still within the ballpark. Really, I found a nice little reference on the SPSS website right here, where they talk about, they actually give you sort of some rules of thumb. So KMO values less than 0.5 would be those that might require sort of remedial action. KMO values greater than 0.8 can be considered good, and an indication that the component or factor analysis will be useful with the variables. And I've also seen, values, at our suggestions or rules of thumb at 0.60 or above would be considered reasonably, kind of acceptable, although it is still on the low end. So in our analysis right here, we see that the KMO value is falling pretty much at 0.6, maybe a whisper below. So it's not really an ideal sort of situation. But we also have Bartlett's test of sphericity, and this is basically testing the difference between the correlation matrix for our variables and an identity matrix. So the identity matrix is just what I was telling you about, which is it has ones along the principal diagonal and zeros along on the off diagonal. So I'm not going to draw all of these in here, but basically, what we have is our sample correlation matrix, or sample R, I guess you could say, and we have the correlation matrix for essentially an identity matrix. Let me just kind of move that off of there. And we have an identity matrix, and really what we're trying to do is test whether the observed correlations follow an identity structure or whether there's a significant difference. And so if this test is indicating statistical significance, then we would infer that our correlation matrix for our measured variables is significantly different from an identity matrix, which would then be consistent with the assumption that the matrix should be treated as factorable. So we do have this kind of situation here with Bartlett's test, as our p-value is, we could say p is less than 0.001, assuming a common alpha threshold of 0.05. So clearly our p-value is suggesting statistical significance. So at any rate, we'll move on and we'll look at a couple of other things. So we have in this table right here, we have our components. And so the number of components that are extracted originally, prior to deciding on how many to retain, the number of components that are extracted is going to equal the number of measured variables. And so each one of these has an eigenvalue associated with it. So an eigenvalue is just basically summarizing, eigenvalue is basically summarizing the amount of variation in the measured variables that's being accounted for by a given component. So the components are extracted such that, originally we have correlated variables, and the components are extracted such that we are summarizing variation and it's additive. So in other words, the components are orthogonal to each other and they explain a certain percentage of variation or a certain amount of variation in the measured variables. So you can see right here that these eigenvalues, and the eigenvalues are basically sort of like variance estimates are kind of indicating how much variation is being summarized. So an eigenvalue of 2.419 means that the first component is summarizing as much variation as 2.4 of the original measured variables. The second component is accounting for as much variation as roughly 1.4 of the measured variables, whereas component 3 is accounting for less, basically roughly 0.86 of the original measured variables. So you might be asking, how does this work where we have these fractions here? And you have to keep in mind that the measured variables, the components don't, it doesn't work like, component is accounting for all of the variation here, and all the variation here and all the variation here, and then stops, and then the others are left alone. Really, you have to think about it as, component 1 might explain, this much variation in the first variable. It may explain, more variation in the second variable, and maybe just a whisper in the third variable, and so forth. Whereas component 2 may account for a little bit more variation in 1, and a lot more variation in 2, and so forth. So the variation is distributed over the variables, and so that's the way to think about the variation in this sense. So now, so you can see now where the eigenvalue rule cutoff, or the eigenvalue cutoff rule comes into play, where we were saying before that an eigenvalue less, we would retain those components with an eigenvalue that is greater than 1. Basically, the rule is indicating that we want to retain those components that explain at least as much variation as a single measured variable. So any component explaining less, as much variation as less than a single measured variable, we want to shave off and treat as essentially unimportant. So you can see over here that this is the based on the retention using the eigenvalue cutoff rule. And so in this case, we retained the first two components from the initial extraction. You'll see over here with the initial, so this is the initial side of things. And so with the initial extraction, you also have the percentage of variance accounted for. So the first component accounts for about 40% of the variation in the measured variables. The second one accounts for an additional 22.8%. The third one, 14.39%, and so forth. So you can see that the components are extracted. Not only is the variance accounted for additive because the components are uncorrelated or orthogonal to each other, but also the amount of variation accounted for is decreasing from one component to the next. So as we move to higher level components, the higher level components are accounting for decreasing amounts of variation. So that's why component 1 is accounting for the greatest percentage of variation. Component 2 accounts for the next largest proportion of variation, and so forth. So you can see that based on the eigenvalue rule, cutoff rule that was a default when we went through the menu system, you can see that we retained the first two components, and we had the percentage of variation, which also is going to correspond to this information here. And then we have a column containing cumulative percentages. So prior to rotation, the cumulative percentage will add up to 100% of the variation in the measured variables. Whereas after we decide on how many to retain, if we use the eigenvalue cutoff rule, we have two components that are accounting for about 63% of the variation in the measured variables. So there's pretty good indication, at least using that rule, the eigenvalue cutoff rule, that we would want to retain two components. Also, we could look at the Scree plot, which is essentially a plot of the components in terms of the numbers against the eigenvalues. So essentially the information that we had contained in these first, these columns right here, where we have the component number and the eigenvalues, this is a Scree plot, and it represents a plot of that information. And so it's called a Scree plot because it looks really like the side of a mountain. And so if you look at the side of a mountain, what happens is that at the bottom of the mountain you see that things sort of level off, and maybe they're still decreasing slope. So the slope is more pronounced over here, but then as you move towards this region right here, getting at the rubble of the at the bottom of the mountain, or the Scree, you can see things sort of leveling off. So that's kind of the idea behind a Scree plot. Now this looks really nice, but sometimes you can also have Scree plots that look like this. If I was plotting it out, I could have something like that, and then this, and then something like that, and then maybe a trailing off here. So it doesn't always look as kind of pristine as this, but you can see the basic idea is what you're looking for is the elbow where things sort of level off. So you can see that the first component is that's a given. There's at least one component. The second component is right here, and then you see sort of almost a leveling off at the elbow right here. It's not perfect, but you can kind of see that, and so I can see how one might interpret this. I can just essentially make a cut, if you will, and say that that this might suggest a two-component solution. But sometimes it's a little tricky to interpret, and that's why the Scree plot is criticized for its subjectivity. One other strategy that you might adopt is parallel analysis, and so with parallel analysis, essentially what it involves is using a simulation approach to determining the number of components or factors, if you're running a standard exploratory factor analysis, to retain. And essentially what it involves is generating random correlation matrices. You can see right here the description is generating random correlation matrices, and then generating the eigenvalues from each of those correlation matrices, plotting essentially a distribution of the eigenvalues, and then using a certain cut point to plot against the eigenvalues that you observe in your data, and then from that you can determine how many components to retain. So this website right here is a nice little parallel analysis engine, and you can go right here to get to get there. There are various utilities online that you can use. Unfortunately, SPSS does not have a utility available, so you have to kind of if you want to use parallel analysis, you have to utilize a different approach. So this is a recent engine that I found online, so you can certainly use this. There's also some syntax, SPSS syntax online that was put up there by Brian O'Connor, which is also really handy. So either approach will work. So you can see over here in terms of using the parallel analysis, first it says number of variables in your data set to be factor analyzed. So in our data set, kind of going back, you can see that we had 6 measured variables, and our sample size was 100. So what I'm going to do is I am going to go to the website, and I'm going to put 6 for the measured variables, and sample size, it actually has the default of 100. So you can see also the type of analysis. It says principal components, and I can decide on how many random correlation matrices to generate. I could, the default is 100. I could set it at 1000 if I want, and it will update based on that. And then you can see it says percentile of eigenvalues. So one strategy is to use the mean of the eigenvalues, the distribution of the eigenvalues, but a more really kind of more stringent approach is to use the 95th percentile eigenvalues and essentially compare these against those from your data. So these are essentially randomly generated eigenvalues that we're essentially plotting against or eigenvalues from randomly generated matrices, for that matter, and these are plotted against the eigenvalues from your data. And for those components where the if I have essentially my eigenvalues from my data, if I have something like this where those eigenvalues are kind of decreasing in this kind of way, I can plot the eigenvalues from my data against these eigenvalues. So as long as the eigenvalues from the random data are below the eigenvalues from my actual data, then I'm going to retain the components from the my solution. But at the point at which the randomly generated eigenvalues exceed those that are generated from the data, then I'm going to cut those other components out. So you can see right here that the first eigenvalue is 1.48. So if I look at my data, my output for the eigenvalues, it's 2.419. So I'm at least going to retain the first component. The second eigenvalue is 1.27, and that is less than the 1.369 that I have right here. So you can see that we had essentially one. Let's see, what was the first one again? It was 1.48, then 1.27. So 1.48 is kind of right around here, and then 1.27 somewhere in this neighborhood right here. So you can see that these are randomly generated eigenvalues. And then if we look to see at the third one is 1.11, and for that third one you can see it's 0.863 from our data. So 1.11 is going to put the randomly generated eigenvalue right around here. So you can see now at component 3, the randomly generated eigenvalues are exceeding those from my data, and so then that would suggest that I want to retain a two-component solution. So this is a little bit more stringent approach to determining the number of components to retain. So at this point, we have determined that we have two eigenvalues, or two components that we want to retain from our solution. And really all of our procedures largely agreed. But there are circumstances where they can disagree. And so it's kind of up to you to determine what kind of, how many components to retain. So once we've determined that, now it makes sense to try to interpret the component loadings. So you can see right here down below we have a component matrix, and the component matrix is essentially containing correlations between each of our measured variables and the components, and we can try to name those based on the pattern of loadings. And so a conventional loading criteria, there are various rules of thumb. You might say a loading criteria, a loading value, a loading in absolute value, I'll just say loading in absolute value that is greater than 0.32, we would use that measured variable to help in naming the component. Another threshold that I've seen is a loading value that is greater than 0.4. So just keep in mind that if you make it 0.4, then you have you would have components that are probably comprised of that are more stable if you have multiple indicators that are loading on that particular component. So this is just a more stringent threshold for retaining certain indicator variables or indicators on that particular component. Now, the downside of using just a straight component matrix is that a lot of times you can end up with a situation like this, where you have this variable loading really highly on both components. And so you can't really determine which component the measured variable is better associated with, because there's not much difference in terms of the magnitude of the loadings. This one right here is loading, pretty highly on this one, but if I use the 0.32 loading, it would also be sort of meeting the threshold on the second component. The same goes for here, really across the board. Probably the most unambiguous measured variable that's loading onto a component is really this WA variable right here that's loading on the component 1. So one strategy that is oftentimes utilized, and really it's pretty standard, is to perform a rotation. So in other words, what we do is we take our coordinate axes for our loadings and essentially rotate those axes. So let me show you what I mean by that. One standard approach to rotating or performing a rotation is Varimax rotation. So I'll show you what I mean by that. So let's go to dimension reduction factor, and under extraction, we've already determined that that we would stick with a 2-component solution. If it were the case that so really if we stuck with the eigenvalue cutoff rule here, we're going to get the 2-component solution regardless. But if it were the case that maybe there was some disagreement between the Scree plot and the eigenvalue cutoff rule, or maybe some of these and the parallel analysis, let's say that the eigenvalue cutoff rule suggested 2 components, whereas parallel analysis and Scree plot, I would have wanted a 3-component solution. In that particular case, then I can click down here and then force a 3-component solution, and then perform the rotation based on the 3 components as opposed to 2. In our case, though, we had 2 components. So we could have forced it, in which case we'll still get the same output as above using these other approaches, or we could just stick with this one and still get the 2 components. So I'm just going to stick with that. Click on Continue, and then go to Rotation. And so you can see we have various rotation strategies. So with the method set at none, which is what we have right here, I can generate a loading plot just so you can see what it looks like. So when I go down here, this is the component plot, and so you can see, and this is prior to rotation. So you can see right here that we have essentially the horizontal axis is component 1, the vertical axis is component 2. We start at 0 on both, and so the loadings that are in that matrix are correlations. So in other words, we would have a correlation of a variable on one component. So starting at 0 and going this direction, these are positive correlations. If we're going horizontal in this direction, on this side we would be observing negative correlations. And then in terms of vertically, we can say that as we're going downward on component 2, these are negative correlations, and then if we're going upward on component 2, then those are positive correlations. So you can see that when we plot out the coordinates, so for SMI we have negative 0.624 and 0.527. So there's SMI right here. So on component 1 it's negative 0.624, and then we had the the vertical positive correlation here. So you can see that when we plot out the coordinates for all of our measured variables, they're falling pretty much in this indeterminate space on both components, really exhibiting largely the same loadings. The most unambiguous one is this work avoidance here, which is loading clearly higher on component 1 than component 2. So what we can do is we can rotate the axes. So sometimes people get the impression that rotation is some kind of voodoo or some kind of playing fast and loose with the data. But what happens is that we leave our measured variables in relation to each other. So we don't rotate these data points, or the relationships between the variables, or we don't change that. What we do is we rotate the axes, so that following rotation, what we end up with is component 1 and component 2. This is kind of a Varimax rotation, where we leave the component still uncorrelated, but now you can see that on component 1, these would be more highly loaded on component 1, less loadings on component 2, and these are more highly loaded onto component 2 and lower on 1. So just kind of showing you what I mean by that, we'll go back and we'll run the factor analysis and click on rotation, click on Varimax, and now we'll just display the rotated solution and click on OK. And so now you can see we have the component matrix, which is prior to rotation and then following rotation. And so now you can see SMI loads negatively onto and minimally onto component 1 and highly onto component 2. The second variable, mastery goals, is loaded low on 1 and high on 2, and perceived utility is low on 1 and high on 2. So these variables right here are doing a really good job of can be used to define or name component 2. So I might name component 2 something like approach motivation or something like that. So, reflecting a tendency for students to seek out academic work or whatever, and because they feel positively disposed, they feel an approach motivation. Whereas you can see anxiety, performance avoidance goals, and work avoidance are loading more highly onto component 2 as opposed to component 1. So these might be, I might name this component something like avoidance motivation. So we can name that. So that's the basic idea behind this process. So if we rotate the coordinate axes, then that helps to kind of clean up oftentimes the component matrix so that we can give meaning to the components. We can name them. So that's what a Varimax rotation does for us. And then I'll show you up here another little piece of output that you want to be familiar with are the communalities. And so communalities are basically essentially indicating the proportion of variation in each of your measured variables that's accounted for by the components that are retained. So you can see right here the initial communalities are all 1, and that's because we have all of the components are being used to explain 100% of the variation in those measured variables. Whereas the extraction communalities, you can see right here, this is based on the 2-component solution that are summarizing 63% of the variation in these variables. So we can say that based on the 2 components account for about 71.3% of the variation in SMI. They account for roughly 50% of the variation in mastery goals, 62.6% of the variation in perceived utility, 81.5% of the variation in anxiety, 72.3% of the variation in performance avoidance goals, and 41.2% of the variation in work avoidance. So another indicator that there might be problems with a certain variable that's included in your model is a circumstance where you have a variable with a very, very low communality. So if your factor or your component solution is accounting for really fairly low or trivial amounts of variation, then that would be an indicator that that variable may be problematic to include in that analysis. One final thing that I want to mention before I stop this video is, the rotation that we performed was Varimax, and that, like I said, if you can kind of think about it this way, that previously we had our components. The plot of our components looked like this, and so this is prior to rotation. Then following rotation, you can see that our components remain uncorrelated with each other. But in this case, you can see that the relative the relationships between the measured variables and the components are among the measured variables are the same, but we've rotated those axes. So that's why this group is loading higher onto 1 than 2, and this group is loading higher on 2 than 1. And there are other options as well, because one of the limitations of Varimax rotation or any kind of orthogonal rotation is it makes the assumption that the components are uncorrelated with each other, and that's oftentimes not an accurate reflection of reality. Well, it's never 100% accurate reflection of reality, because everything's correlated to some extent at some level. But where this could be particularly problematic is if in reality the relationship between the variables or between the components really ought to be allowed to be non-zero and be more highly related. So I'll show you another option, which is to go under factor here, rotation. And I can click on Promax rotation, click on continue, and on OK. And so now in this particular case, you can see that we have our solution. And one of the things to note up above is that when we rotated, we essentially have rotated squared loadings. And so we redistributed the variation accounted for by the components into orthogonal rotated components. So the eigenvalues don't look the same after rotation as before. the percentage of variance accounted for by the components is exactly the same, but the distribution of the variance accounted for looks a little differently. It looks like things are a little bit more spread out in across the components in terms of the variance accounted for. So when we look down below and look following Promax rotation, you can see that we have we have the eigenvalues for the rotated components, but there's no percentage of variance accounted for by each of them, and so forth. And that's because we have correlated components, so they share variation with each other, and so we can't treat it as additive like we did over here prior to rotation. So other things to look at, we have two matrices to look at. We have a structure matrix, which is essentially the correlations between each of the measured variables and the components, and we would interpret it in exactly the same way that we did before when we utilize Varimax rotation. So these are all zero order correlations. So you can see once again these variables are correlated most highly with component 2. These are correlated more highly with component 1. So it pretty much mimics what we had before. The pattern matrix reflect, these are very much analogous to partial regression coefficients. So if you think about it, after rotation, we have component 1 and component 2 that exhibit some level of correlation, and each of those components are associated with each of the measured variables. So like, this might be SMI, and so in this particular case, because these variables are correlated to a certain extent, when we look at the relationship between a given component and the measured variable, then we're controlling for or partialing out the variation associated with the other component. So these are so that's how you can look at these. The pattern matrix is, can be handy to identify those variables that are most highly related to the component. But my general recommendation is to kind of focus your interpretation mainly on the structure matrix, although you can use the pattern matrix to sort of supplement and better inform your components when you're naming them. Down below, you can see we have a component correlation matrix. Component 1 and component 2, they're correlated at negative 0.261, which is what you would expect. Basically, component 1 was essentially reflecting avoidance motivation, whereas component 1 is reflecting an approach motivation. So you would expect a negative correlation between those two components. So at this point, we've identified the number of components, we've named them, and with our data set, we do have a variable achievement. So let's say I want to take those components and predict achievement. So one of the things that I could do is I could maybe use the transform function, compute variable function, and create new composite variables that reflect approach motivation, maybe averaging across these subscales right here and coming up with a composite measure of approach motivation and average across these and come up with a composite measure of avoidance motivation. Another option that you might consider is to rerun the analysis. I'm going to go ahead and just I'll stick with this. And you can generate component scores, which are essentially scores for each case for each of the components that are retained and have been rotated. So if you click on Save as Variables, Method Regression, we'll click on Continue and then on OK, then what SPSS will do for you is it will generate these component scores. I know it looks like factor scores, but that's just the naming. So we know that the first component is called avoidance motivation, and the second one is approach motivation. So I can click on this, and I can call this. I'll just call this avoid, and I'll call this one approach, and I'll get rid of the label. And now I'm ready for business when it comes to predicting achievement. So I'll just run really quickly a regression analysis with achievement as the dependent variable and these two variables as predictors. And when I run the analysis, you can see that the R-squared value is 0.231. It's statistically significant. And you can see that avoidance was negatively predictive of achievement, although it was not significant. So we're going to infer that there's no relationship between avoidance and achievement. Whereas we see that approach, there's a positive predictive relationship between approach motivation and achievement. It's statistically significant. And if we want to compare those two components in terms of their relative contributions, you can see that, just take the absolute value and you can rank order them in terms of their contributions. You can see that approach motivation was really doing most of the work when it comes to predicting achievement. So that's a good example of using PCA for data reduction in order to incorporate it into a later analysis. So we just basically, to summarize, we basically generated a PCA solution. We determined that two components would best summarize the variation in the measured variables. We then named those components approach and avoidance motivation. And then we generated component scores and then utilized those component scores as predictors in another analysis, our regression analysis predicting achievement. So that pretty well provides an overview of PCA and some of its uses and so forth, and a lot of the strategies that are involved. It's kind of a long video, but PCA and exploratory factor analysis by the same token, these are complicated procedures, so they're not something that you can just summarize in about a 10-minute video very effectively. So I apologize for the length of the video, but I want it to be reasonably comprehensive. Also, I have my door open, so if you've been hearing birds tweeting in the background, those are coming from my backyard. So at any rate, I hope you found this video useful, and have a good evening.